So a very good day, doctor. So my name is Yong Sin Yi and matrix number S70959. So today I'm gonna to present my chosen journal for organometallic compound chemistry assignment, which is synthesis of organometallic ruthenium 2 and iron 2 complexes containing fused rings, hemihelical ligands as chromophore, and evaluations of nonlinear optical and LO properties by HRS. So this is the structure of my compound in the selected journal. So the metal center is an iron atom and it has 3 ligands. Alright, before we get into the naming of IUPAC name of the compounds, we need to calculate the oxidation state of the ferrum metal atom. So according to the formula, so we can calculate the oxidation state of Fe by applying in the mathematic equations. So the whole cation complex is equal to positive 1 charge, and then for the ligand, cyclopentadienyl, we have 1 electron, and DPP and nitrile ligand is actually neutral ligand, so 0 electron. So and applied the mathematic into the equations, we get iron equal to +2. So the oxidation state of iron is actually iron 2. Alright, so the next step we get to naming is that we need to name for all the ligand in the complex. So we have 3 ligand in this complex. The first one is C5H5, stand for cyclopentadienyl, and the second one is DPPE, we name as 1,2-bis diphenyl phosphinoethane, and the last one, the nitrile ligand, we name as benzo 1,2-B 4,3-B prime dithiophan 2-carbonitrile. Alright, so finally we get into the naming of the complex. So the IUPAC name of this compound is mu5 cyclopentadienyl 1,2-bis diphenyl phosphinoethane benzo 1,2-B 4,3-B prime dithiophan 2-carbonyl iron 2 hexafluorophosphate, and we name as iron 2 as the oxidation state is +2, and the 3 ligands we arrange in alphabetical by their names, okay, but we eliminate for the prefix, so we get the name like we have C, we have P, and then we have T for 3 ligand. And last we have counter ion, which is the PF6, the hexafluorophosphate. So it is an ion, so we need to put it after the cations. And the overall charge is balanced because the metal complex is +1 and the PF6 is -1. So the whole complex is neutral charge now. Alright, so after naming, we get into synthesis or preparation method. So this complex were prepared by halide abstractions from the neutral parent complexes. So the neutral parent complexes is actually do not contain nitrile ligand, but we do contain iodo ligand. So we use 1 millimole of the parent complexes and 1 millimole of thallium hexafluorophosphate in acetone, and in the presence of a slight excess, maybe 1.1 millimole of the nitrile ligand, and go for reflux for 16 hours under an inert atmosphere. And then for the second step, after the reflux, we need to cool to the room temperature, filter and removing the solvent. So now the complexes were washed with the hexane 3 times for 50 ml and recrystallize with acetone or heptane or hexane, giving the crystalline products at the end. Alright, next we get into type of reaction of this compound. So according to the process that we have discussed just now, the reactant is the parent neutral complexes, which we do not have nitrile ligand, but we do have iodo ligand. So in this state, iodo ligand actually contribute 1 electron, and finally we achieve 18 electron rules in the first reactant. And for the intermediate, which means after the halide abstractions, so the whole complex the whole complexes exist as positive charge, but in the electron counting rules, positive charge stand for minus. So we minus 1, so we get 16 electrons. And the last one, for the product, we have already substituted the nitrile ligand, and the nitrile ligand contribute 2 electrons, and we do achieve again the 18 electron rules here. So the reaction is considered to be a ligand substitution because the number of ligand from the reactant to the product is just the same, is 3 ligand over here, and we have the same electron for the reactant and also product, which is 18 electron. So in this state, we actually consider as normal ligand substitution, but not associative or dissociative, as the electron number is just the same. Alright, so we get into the last part, which is the applications of the complex. So I found 2 applications in this journal, which is NLO, nonlinear optical materials, and SHG, second harmonic generation. So these 2 terms is actually mentioned in the first slide for the title just now. So it is very important application in this journal. So we get back to the first one. So the NLO, the ion exhibits significant NLO properties because of its high hyperpolarizability. Okay, so we get back to the number 1. So the ion is measured via hyperrelay scattering, and we found that it exhibits the significant NLO properties because of its high hyperpolarizability, we mentioned as beta. And then we get to the number 2, SHG. So this beta is very important. When the beta value is high, it enables frequency doubling, converting infrared lights to visible light. So this is a very important key of NLO application in this journal. Alright, so we get into the end of the presentation. So that's all from me. Thank you for listening. Bye.